Here we are with our video for section 3 of chapter 8, which is essentially referred to as gas stoichiometry. Here are the learning objectives, so please pause your video and write these in your notes. One of our first objectives here is to utilize the ideal gas law to help us identify gases with values that we've worked with already in this course, like density and molar mass. So first, let's look at molar mass of a gas. If I think for a second about how we utilize molar mass, we commonly used it in a grams to moles conversion. So if I had some value of grams and I wanted to convert to mole, I would end up doing this using the molar mass in grams. Okay. So if I think about what really I'm doing here is I'm dividing the grams by the molar mass. If I abbreviated that differently, which I've done here, I use the lowercase m to signify grams and the capital M to signify molar mass. So we know that moles equals grams over molar mass. So, and I can then substitute that in for the N value in our ideal gas law equation, which I've done here. Relationships will allow us to solve for molar mass, and then if I have a molar mass and it's an elemental gas, I can look it up on the periodic table, or I could use that molar mass to help determine things like the empirical formula. Next is to utilize the value of density. And as you recall, density is an intensive property, which means it does not depend on the amount of substance, but it will depend on, with regards to a gas, these concepts of pressure, temperature, and molar mass. Based on what we just talked about with regards to molar mass, if we think about the formula for density, which is mass divided by volume, along with this concept that we just looked at with regards to molar mass and the ideal gas law, if I put those concepts both together and rearrange, I'm able to come up with a formula for calculating density of a gas. And that looks like this. So density of the gas is the molar mass times the pressure divided by the gas constant, is the temperature. As always, as we continue to expand our knowledge of chemistry and add new concepts that are linked or overlap, we have to continually think to ourselves as we start a problem, what is this problem asking for? What is this problem giving me? And then think about how to plan that solution to connect those two dots. Next, let's talk about stoichiometry and gaseous reactions. So here we're going to combine the stoichiometry work that we've done in prior units with the gas law work that we've done in this unit. Clearly, the stoichiometric factors, if it's stoichiometry, I'm talking about the coefficients in the balanced equation. They are going to have an impact, that molar ratio. Additionally, so will the ideal gas law. Here are an example of two different types of gas stoichiometry problems. So I'm going to pause the video here for a second, take a look at these two problems and see if you can identify what is different in each problem. You may have noticed in the first problem, we have a reaction that is at standard temperature and pressure, or STP. And in the second reaction, we have a pressure and temperature given to us. This is the distinction between the two types of gas law problems. We have some that are at STP, and we have others that are at pressures and temperatures different from STP. And how we approach these is going to be slightly different in each case. Let me review for a second our mole map which I introduced earlier in the year when we were doing conversions through the mole. At that point in time, we really focused on these conversions, the relationship between grams in mole and particles in mole. I'm going to add a piece here to our mole map, which for gases, I can convert to volume or liters of gas using 22.4 liters. This is known as molar volume of a gas. And the molar volume of a gas works if and only if our gas is at STP. At STP. If we have a gas at STP, then really all it becomes is a stoichiometry problem using the fact that 1 mole equals 22.4 liters of gas. If our gas is not at STP, we have to use the ideal gas law equation to account for that difference in temperature and pressure. So let's take a look at these two problems. The first one is at STP. Before I get started, I know the first thing that I need to do is balance this equation. So go ahead and pause the video to balance this equation. Here's how you should have ended up balancing that equation. So because this problem is at STP, this just becomes a 3-step stoichiometry problem from grams of NH3 to volume of nitrogen dioxide gas. So as always, I would start with my 50 grams of NH3. I think about my roadmap. I need to first go from grams to moles. I would use the molar mass of NH3 here. And the molar mass for NH3 would be 17.03 grams. Here is where I would be converting from moles of NH3 to moles of the substance they're asking about, which in this case is the nitrogen dioxide, NO2. As you recall, in our stoichiometric relationship here, or our molar ratio, these values are going to come from the balanced equation, 4 and 4. And now I can convert from moles of NO2 to liters of NO2 using the molar volume of a gas, 22.4 liters. We would get 65.8 liters of NO2 as our answer. So that's what I am allowed to do if it's at standard temperature and pressure. I can use the molar volume of a gas, 22.4, as a conversion factor from moles to liters. Now, what happens if my gas is not at STP? Well, if it's not at STP, we have to use the ideal gas law equation to account for those differences in pressure and temperature. So if I think about what the problem has given me and what the problem is asking for, I have a pressure, 1.50 atm. They're asking me for a volume. I have an amount, but I need to be careful here. Here's where the stoichiometry comes in. I have an amount in grams of potassium chlorate, but the question is asking about oxygen gas. So I can't fill in my N value just yet. I know our gas constant, and I have a temperature of 25 degrees Celsius. So when I convert that to Kelvin, I would get 298.15 Kelvin. So that's where the gas law comes in. This is the gas law part of this gas stoichiometry problem. I'm going to use the ideal gas law. But once again, these values that I'm having, this is the pressure of oxygen gas. This is the temperature of oxygen gas. and we have the gas constant, and they want to know the volume of oxygen gas. My amount, my N value, my moles, the only thing I have to get there is the 10.5 grams of potassium chlorate. So here is where our stoichiometry comes in, because if I have 10.5 grams of potassium chlorate, I can convert that to moles of oxygen gas. Okay, so first I'm going to use the molar mass here, 122.5 grams of KClO3. And then I'm going to do my molar ratio step, and I'm going to go from moles of KClO3 to moles of O2. Now, before I can fill that in, I obviously have to go back here and balance my chemical reaction. So my chemical equation, if I put a 2 there, a 3 there, that balances my O's, and then that balances my KCl. So my ratio here is 3 to 2, and now I can solve for moles of O2. We would get here 0.129 moles of O2. That can then be plugged in for my N value for the ideal gas law equation. And now I'm able to solve for the volume of the O2 gas. If I do that work there, I would get the volume would equal 2.10 liters O2. So there's the difference between gas stoichiometry at STP, where I can just use molar volume of the gas, and a gas stoichiometry that is not at STP, so I have to use the ideal gas law equation to account for those different temperature and pressure values. Finally, let's finish this section off by talking about Dalton's law of partial pressures. Dalton's law of partial pressures just states that the total pressure of a mixture of gases would be equal to the sum of the partial pressures, as you can see in this diagram I've provided. That if I mixed all these gases together, they all have their own pressure, but if I mix them together in one vessel, the total pressure of this combined gas, this solution of gases, would just be the sum of those three individual pressures. You can have Dalton's law of partial pressures problems like the first one listed here, which are pretty straightforward. It's just the idea that I'm going to add up the pressure of the gases combined. So oxygen and chlorine gas are mixed in a container with a partial pressure, 401 millimeters of mercury and 0.639 atmospheres. The issue here is that I cannot add these two gases because they're not in the same unit. Since the problem is asking to have it in atmospheres, I'm going to convert the millimeter of mercury value to atmospheres. If I go back to our standard pressure values and how all of our pressure units are equal, I would see that 1 atm is 760 millimeters of mercury. So I can pretty quickly convert millimeters of mercury to atm. We get 0.527 atm. Now the total pressure is just the sum of our two partial pressures, are two of oxygen and chlorine respectively. So that would be 0.527 atm plus 0.639 atm, and our total pressure is just 1.166 atm. So those are going to be pretty straightforward, maybe some pressure conversions here and there, but you can also imagine that we can get a little more complicated. So here, before I can get to the point of answering my question, what will the pressure of the resulting mixture of gases be? So before I can get to that point where I can get the total pressure simply by adding the pressure of N2 plus the pressure of O2, my two gases here, I have to get those pressure of O2 values and the pressure of N2 value using the data in the problem. So you'll see here that we have 45 grams of N2, 115 grams of O2, and both of them are in a 35-liter container at 25 degrees Celsius. So I can solve two ideal gas law equations here where we get the pressure of O2 is going to be equal to the moles of O2 times the ideal gas law times the temperature, which is the same for both, over the volume, again, which is the same of both. And then I could solve for the pressure of N2 using, again, the moles of N2, which I would have to do my mole conversion, the R, and again here the temperature is the same for both, and the volume is the same for both. So at this point, I could use my ideal gas law equation to get those pressures before I then take those two pressures and add them together to get my total pressure. It's just an extension of the gas law work we've already been doing. I just wanted to point out that Dalton's law of partial pressure problems are not always going to be just simply adding or subtracting to get the whole or the part. There may be an occasion where you have to apply what we already know to get those pressures before we simply add them together. All right, that's the end of section 3 here, gas stoichiometry. Now we'll do some practice.